The last type of collision we're going to worry about is called an elastic collision. So perfectly elastic collisions conserve both momentum and kinetic energy. Now, all types of collisions conserve momentum. All types of collisions conserve momentum as long as they're isolated. But only perfectly elastic collisions also conserve kinetic energy. So what does it look like? We have two objects that come in, they're moving separately, they collide, afterwards they rebound, sometimes in opposite directions, although not always. But if you look at the total kinetic energy of the system beforehand, it will be equal to the total kinetic energy of the system afterwards. So momentum is conserved and kinetic energy is conserved, where my initial event is before the collision, my final event is after the collision. So in terms of if I just had two objects like this, my momentum conservation equation would look like this. And my conservation of energy equation I could write would look like this. Okay? Make sure that these all make sense to you. Now, if you knew your masses and you knew the initial for both objects, V1 initial and V2 initial, then you would have two equations with the same two unknown variables. V1 final would be unknown and V2 final. And those two unknown variables show up in both these equations. So in theory, you have two equations and two unknown variables. You should be able to solve that using simple algebra. The algebra, in fact, is not simple. It's actually quite annoying and tricky. So rather than having you every single time you get an elastic collision problem, rather than having you have to solve this crazy system of equations, I think it's better in this case to just have these equations written down, to have these are solved for you. Okay, so this equation here lets you calculate the velocity of one object after a perfectly elastic collision based on the two masses and what their initial velocities were. So you can write down both of these equations. You really only need one of these equations because they're the same equation, just with the M1 and the M2 switched, right? Wherever there's a 1, make it a 2, and that gives you the other guy's velocity, if that makes sense. If you're not sure what I mean, just write down both of them. But again, when you use this equation, you've already taken into account that kinetic energy is conserved. And you've already taken into account that momentum is conserved. That's where these two equations came from. They came from these conditions that momentum is conserved and kinetic energy is conserved. So since we're talking about energy, let's kind of bring it in more formally into our discussion about collisions. So first of all, during any type of collision, I want to remind you, as long as it's isolated, there's no external forces, then no matter what, momentum will be conserved. Now, if you have an inelastic collision, you're going to lose kinetic energy. Kinetic energy doesn't disappear, it just turns into some other form of energy. So, very often your kinetic energy can be transformed into heat through friction. You can lose it to deformations, like if you have two cars and they crash and they stick together afterwards. There's, believe it or not, there's energy stored in the crumpling of the cars and then the mechanical deformation of the metal. But wherever that energy gets transformed into, I'm not as concerned with that. But I just want you to recognize that kinetic energy is lost in an inelastic collision. In an explosion or a reverse inelastic collision, you end up with more kinetic energy than you had before. Think about the case with a gun. So initially, if you have a gun and a bullet, the total kinetic energy initially is 0. And then afterwards, you have a bullet going in one direction really fast, and you have a gun recoiling in another direction pretty fast. So you're gaining kinetic energy. And I think it's often interesting to be like, well, where did that energy come from? In the case of a gun, I would say there's chemical energy in the gunpowder that gets transformed into the kinetic energy after the explosion. Okay. So those are those two types of collisions. And then in an elastic collision, kinetic energy is conserved. Okay. So this kind of helps you think about what's happening in terms of energy and the kinetic energy of the objects involved in our collisions. Now, the one other little thing we need to worry about when we're talking about energy is whenever you have a collision, you really need to make sure that momentum is conserved. And so if we have problems where there's a collision, like in the middle of the problem, and we're going to go through some examples after this, you need to always have an event right before the collision and right after the collision. So even if it's a problem like, and we're going to look at a problem like this in a second, like Tarzan's on top of a cliff, he swings down on a vine and he picks up Jane at the bottom of like a ravine or something, and then he swings back up. And I want to know, how high does he get? I can use conservation of energy to figure out everything that's happening. How much potential energy does he have at the top, and that gets converted into kinetic energy at the bottom. To everything before the collision, I can use conservation of energy to get there. Okay. And then maybe there's work being done, or I'm not sure if there's work or anything like that. But then you need to have an event right before the collision and an event right after the collision, and you need to make sure the momentum is conserved before the collision to after the collision. And then after the collision is over, you can go back to looking at conservation of energy. Okay, so keep this in mind, and the point I'm making here is anytime you have a collision, you need to have an event right before the collision, and you need to have an event right after the collision. Always, always, always. And I'll point that out in the examples that we do after this.